Now, when we get to a sphere, we don't have any simple principles that we can use to reason out the formula for its volume. So we're at the level of this course, at least, if we have a calculus course, there's an easy way, relatively easy way to calculate the volume of a sphere to get the formula. But at this level, that's not going to be the case. It's not even all that easy if you know your calculus. So the volume of the sphere is 4/3 pi r cubed. That's just a formula. You have a sphere of radius r. So this represents a sphere of radius r. And the surface area of the sphere is 4 pi r squared. Okay? And that can actually be a little easier to remember than this. And once you've remembered this, it's not all that hard to go to this. You got that 1/3 in there and another power of r. I'll make a connection. This doesn't prove anything, just a way that might be helpful if you need to remember this formula. I can draw a circle which includes the center of the sphere. So we have, I call this a centered circle. That's a circle whose center is the same as the center of the sphere, so its radius will be the same as the radius of the sphere. And that circle then clearly has radius pi r squared. The surface area of the sphere is 4 times that. It's 4 pi r squared. So it's 4 times the area of this circle here. So you take the area above this circle, it's going to have an area, the surface of the sphere will have an area that's equal to double the area of this circle. And below the surface of the sphere also has an area that's double the area of this circle. So if that's helpful to you, it's not a bad thing to remember and think about. Again, the reasoning, the Greeks figured all this out. The Greeks figured out these formulas, but they used some pretty sophisticated geometric reasoning that we're not going to have time to get into in this course. Okay, a cylinder. Okay, we have figured out how to find the volume of the cylinder, area of the base times its height. That would be pi r squared times h. The area. Okay, well, a cylinder has a top and a bottom. The top and the bottom have areas pi r squared. Top area is pi r squared, and that equals the bottom area. What about the area of the sides? Well, as we've seen and as I demonstrated and as I can demonstrate again, here's a cylinder. Okay, nice cylinder. Okay, if I cut the cylinder along the side, let's say along this line here, and unravel it, I get a rectangle. Okay. So I can cut the cylinder here, unravel it, and I get a rectangle. What are the dimensions of that rectangle? Well, the width of that rectangle is equal to the height of the cylinder, the altitude of the cylinder, and the length of the rectangle is equal to the circumference of the cylinder, because it's the circle here that unwraps to form this, the length of this rectangle. So it's very clear then that the surface area of the curved portion of the circle is going to be the equal to the circumference of the base times the height. The circumference of the base is just pi times its diameter, which is 2 pi times its radius, so that this area is going to be 2 pi r, the length, by h. So the area of the curved surface is 2 pi r times h. And that's not a formula that's handed down on a stone tablet. That's a formula that's very easy to figure out. One that's a little less easy, and I'm not going to complete the argument because we have to get into sectors of a circle and so forth, and we could do that, but in the interest of time, we're not going to. We have a cone, okay, base radius r, height h. How do we find the surface area of that cone? Well, if we cut the cone here and spread it out, what we're going to get is a sector of a circle. Okay, it's going to be kind of like a triangle. People said it would be a triangle. Yeah, it is, but the side is rounded because the distance from the top to any point of the base is always the same, and it's the same as the length of this line here, let's say, along this side of the cylinder. And since that distance is always the same, the distance of all these points from here is always the same, and the figure that has the same distance from this point, the figure for which the distance is always the same from this point, is a circle. So this is part of a circle, and it's got a rounded side here. Being part of a circle, it's not going to be too hard to find its area if we can figure out its radius and if we know how much arc we have. Well, the distance along the arc here is equal to the circumference of the base, because the whole circumference of the base is what unwraps to give you this arc, and the arc has arc length 2 pi r. What's the radius of this circle? It's not equal to the radius of the base. It's not equal to the altitude of the cylinder. But if we look at a cross section, if we just look at the cylinder from the side, we see that it's going to be the length of this line, which is the hypotenuse of a right triangle whose altitude is h and base is r. And using the Pythagorean theorem, we find that this length is square root of h squared plus r squared. So now we know that this is an arc of a circle whose radius is h squared plus h squared, and the arc length is 2 pi r. And from that, we're going to be able to reason out the area of the cone, and that's where the formula that you see in your book for the area of a cone comes from.